Okay, so today's topic is hash tables.
Yay.
So this is one of the most commonly used, most important data structures that we will study. So we are going to start by reviewing a little bit of information about how information is stored in a computer, because we're going to have to start doing things kind of like at the bit level with this project. So for those of you who haven't had computer systems, here's a little intro to how information is stored. So you know that in this slide here, we have the hexadecimal abbreviation for binary values. So you know that all information in a computer is stored in binary. In other words, as a string of ones and zeros. So this hexadecimal abbreviation is just a way to store binary patterns so that we don't have to write them more compactly. It's a way to store them more compactly so that we don't have to write out all the bits. So you see there are 16 hexadecimal characters starting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. And each one of those letters just is an abbreviation for 4 binary values. You see, so 5, when you see a hexadecimal 5, that stands for 0, 1, 0, 1 in binary. So it's just an abbreviation, that's all it is. And you see the letter F is 1, 1, 1, 1. That just stands for 4 ones. Okay, so that's just a hexadecimal abbreviation. So frequently in this material that we're going to do today and tomorrow, we will just use this hex abbreviation, but it's just an abbreviation for binary. But ultimately in the computer, everything is stored in binary. Oh, by the way, so a binary, a bit stands for binary digit. Okay, so the word bit stands for binary digit, and a binary digit is 0 or 1. Are you with me? So, and then you guys know a byte. We don't need to know this for here, but a byte is what? How many bits? 8. 8 bits. So right away, how many hex letters does it take to indicate the value of a byte? It takes 2. Are you with me? Is everybody clear? So that's just a little fact. Now here's another little fact. How integers are stored in binary. Now you know in decimal, if you have this number like 563, you know this 3 is in which place? The 3 is in the ones place. This is in the what? Tens place, and this is in the hundreds place. So it works the exact same way in binary, only instead of being base 10, where this is ones, tens, and hundreds, in binary you see it's the what? It's the ones and then the what? The 2s and then the 4s and then the 8s and then the 16s and so on. Is everybody clear on that? So the way unsigned binary integers are stored is using this representation. So you see here in part B of the figure we have the binary number 10110. Well, what that means is that there's 0 in the 1's place, 1 in the 2's place, 1 in the 4's place, and 0 in the 8's place, 1 in the 16's place. You add all those up, you get 22. So that's how the number 22 is stored. Are you with me? Now in computer systems we learn about all this stuff and how to do the conversions and how negative numbers are stored. And in computer organization we learn how floating point numbers are stored and all that stuff. We don't need to know all of that stuff. All we need to know here is that integers are stored in binary like this. Okay? Now, the next thing about information representation is how are characters stored. Now in Java and C++ and C, all these C languages, an array of characters is an array of bytes, and there is 1 English character per byte. Are you with me? And in part C of this figure, on this slide, are a few character representations from the ASCII representation of how letters are stored, how English characters are stored. By the way, anybody know what ASCII stands for? I won't write it down, but ASCII, it says here, the ASCII representation. That's basically that's it. It's the American Standard Code for Information Interchange. And it was developed during the teletype era, for exchanging, they would send telegraph messages over phone lines. It came from that, and then when computers came along, it was adopted. It's very common. Here again, you learn about all this stuff in computer systems. But look what we have in this table. We have, on the top row, we have a list of characters. So we have the characters 0, 1, 2, etc. We have capital A, capital B, capital C, etc. up to capital Z. We have some punctuation characters, left bracket, the bash. We have lowercase letters A, B, C, Z, and so you can look up online. There's tables. You can look at the ASCII table. And so whenever we write a string of characters, each letter is encoded like this. Now, on the on the third row is the hexadecimal representation for the letters. For example, let's take a look at the letter lowercase z. So here on the table you see lowercase z. And what is that 7a? On the bottom row, it's the 7a. So what does that mean about the bits of how z are stored? Well, we go back here to our hexadecimal abbreviation. Now, what was that number, the hex number? It was 7a, right? So here, z is stored as 7a. That means literally this z is stored how? 0, 1, 1, 1, and a is what? 1, 0, 1, 0. So this is how the letter z is stored in binary. Now, does everybody just understand how that works just by looking up on a table? Are we good? And furthermore, this could be interpreted how? This could be interpreted as a what?
A number.
It could be interpreted as an integer, like this in part B. And if this were interpreted as an integer, what integer would it be? Well, this would be the zeros place, this would be the ones, this would be the twos, this would be the fours. So what would this, what would this be? 1, here, let's do it. 2, no 4, 8, 16, 32, 64. And if you add all this up, guess what you get? 122. I think. Somebody do it real quick. I hope the table's right. Does everybody see how that works? So here's the thing, you guys. What this means is that in all the C languages, like C and C++ and even Java, you can actually, it's type compatible. Characters are type compatible with integers. Did you know you can do this? You can say for char ch gets, quote, little a, semicolon, ch less than or equal to z, and then ch plus plus. You can do this. You can add. Here, what are you doing? What are we doing here? Adding 1. Well, if you add 1, it's the next letter over. And so you can run through all the lowercase letters like this. Okay, suppose you say char ch. All right? So ch is type what? Char. Okay, so it's like a single English character. And then you can do this. You can say ch gets, now watch this. You can give it a hexadecimal value. And the way does anyone know how to write down a hexadecimal value in a C program? Oh, okay, well anyway, it's 0, it's 0x. You start it with 0x and then you give the hexadecimal digits. So here, if we said 0x 7a, like this, then ch would get this bit pattern. And then if we do cout, if we stream to the output ch, guess what would come out? The letter z, lowercase z. Now, does everybody see how that works? There's this correspond, because this is hash tables use this. So there's this correspondence between binary and and the way they're stored, and they have integer values. You can add, you can do things to characters just like you can to integers. Yeah.
Why is 0 not just represented by 0?
Oh, that's very good question. See, what happens is there's a difference between the character 0 and the number 0. Are you with me? This is an int, this is a char. It turns out that the ASCII 0, all zeros, is another symbol, is another character in the ASCII table. Are you with me? Yeah, and that placement, like I say, this came historically. This is just arbitrary. So you understand the difference between a character 0 and that was a good, very good question. Yeah. All right, is everybody clear on this? Okay, so we'll be using this with this hashtag. All right, so that's kind of like the basics of information representation in binary. All right, now watch this. This seems, I'm going to ask you a question here. Now watch this. We've talked about dictionaries, right? And what can you do with the dictionary? You can store key value pairs, you can look them up, you can remove them, blah, 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 right? And we had the binary search tree implementation of a dictionary. Now, let me ask you this question. Suppose now, oh, by the way, somebody asked the other day, does the key have to be an integer? And do you remember what the answer was? No, it does not have to be. In fact, it is frequently the case, and in fact, right now, we're going to talk about the situation where the key is a string. So that's numero uno point right here. So consider the following dictionary. The key is a string with a maximum of 8 values, 8 characters, sorry. That's maximum of 8 characters. How can you implement each of insert, remove, contains, in time, big theta of what? 1. Now what does big theta of 1 mean?
This goes through 1 string.
Well, it means not big theta of n, not big theta of log n, big theta of 1. No loops. No, you know how we did the binary search tree? Left, right, find the maximum on the left. No loops, no 1, big theta of 1. Does anybody know? Can anybody think about it? Well, obviously this is not going to be based on pairwise comparison.
Because of the hash. Oh, okay. Sorry.
Yeah. Well, actually, we're leading up to hashing, but obviously it's not going to be based on pairwise comparison. How can you find out? How can you have a situation where you don't have to compare it? You can't do a binary search. You can't do pairwise. How can you do it without pairwise comparison? How could you look up something without pairwise comparison? Seems impossible, huh? You have an idea? Anybody?
Well, you store it like on the key.
Well, the key is an 8, yeah, but how would you store the key? I mean,
doesn't it like convert the key into like the numbers and it stores based on the number?
Well, yeah, the key, that is the idea. The idea is this: what we do is we make the key. We just write those 8 characters a key, and we just consider that to be what? A single number. And then that number can be the what? Well, no, the key value pair. We still have the key value pair, but that number could be the what? How, to look, data? Yeah, but in what data structure?
A list.
Index?
Or
Index of a what?
Array.
Of an array.
Oh my gosh.
Because with an array, you don't. When you go to the element of when you go to an array, to get to like the 51st, sub 51, you don't have to go check that, test all the way through. You go direct. You can directly access an array. So look, here's the situation. Direct addressing. Now look. So what we have here is an array. The name of the array is table. And it has sub 0, sub 1, sub 2, all the way down to sub what? 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,615. Right? Are you with me? And what is that number? That number is 2 to the 64 minus 1. Are you with me? Because look, suppose you want to store the 8-letter word flapjack, and that's your key. what you do is you see those 66, 6C, 61, 70, 68, although each one of those is the character, and each one of those stands for, each one of those pairs is 8 bits. You got 8 of them. 8 times 8 is 64. Are you with me? So there's 64-bit number. And that number, if you convert that number into decimal, it's 7, what did I say, 7... septillion, 308, blah, 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 blah. And then you go to table sub 7380381024222, and boom, there you put it. Yeah.
So the big long number at the bottom, that's like the integer sum of what 6b stands for plus what 63 stands for plus what 61 stands for?
No, okay, what it is if you write that number out all in binary, for flapjack, the 6, what was 0? I mean, what was the hexadecimal 6? Isn't it 110? 0. So it would be 0110, 0110, 0110, and what is the letter C?
1100.
1100, blah, 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 blah. You'd have 64 bits. And then and this is the 1's place, the 2's place, the 4's place, the 8's place, the 16th. That's that integer.
Okay.
And it would be sub that. You go that, and boom, there it is, direct. And if the way you would do quixotic, there's the letters, there's the ones for Q, there's the U, I, the X, O, T, I, C, boom. That's 18. It's bigger, right? Because it starts with a bigger letter. Are you with me? So that's 18 quadrillion, no, what's 5? Quintillion. 18 quintillion, 446 quadrillion, 700, blah, 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 and go right, boom, there. Okay, now, and that's big theta of 1, exactly. No ifs, ands, or buts. Well, what do you think about that? Why don't you go to your boss and propose that? Next time he wants big theta of 1, say, look up big theta of 1. What's your boss going to say?
You're wasting all this space.
Well, not only are you wasting all this space, but what about 18 quintillion? It's not that you're wasting space, it's that it's literally physically what?
Impossible.
Why is it impossible?
Takes too much memory.
What's the size of your memory?
Not that big.
No, not by a long shot. Are you with me? On the other hand, it is big theta of 1 because it's direct addressing. So now, here's the next question. Look. Oh, wait, before we go to the next question, let's take a look at what our algorithms would be. How would you insert key, comma, val? What would you do? Just that. Look. Table sub what? Key gets what? Key value pair. No loop. No binary search. No if left then blah, blah, blah. Are you with me? Does everybody see that that's what that would be? Okay? And here, how would you do remove? Like this, bool, remove, key val. And now what do we, oh, by the way, in order to do this, we would have to initialize our array to have some special empty pair of values so that we could detect that nothing's in there, because we would not want to interpret garbage as being something. Are you with me? So we would need a special key value pair that we could detect that would represent the empty, represent it being empty. And by the way, how long would it take to initialize that? Probably longer than the age of the universe. I don't know. So you physicists know how old the universe is. I mean, be long time. I mean, But anyway, theoretically, we're talking theory here, right? Okay. So if table.key equals special empty, return false. Else what? Val gets what? Table sub key, sub key, index it, dot val, all right? And then table.key gets special empty pair, return true. And then here it's the same thing here with contains. If table.key equals special empty pair, return false, blah, all right? And you just it's direct, big theta of exactly 1. All right, does everybody see how that's theoretically possible, if not in practice? Now, but with that idea, let's think about this. So let's pose this problem. Suppose you have a key as a string with a maximum of 8 characters, but now, instead of doing exactly what we did, how can we modify direct addressing to implement insert and remove and contains in time approximately big theta of 1. In other words, is there a way that we can shrink that table down from 18 quintillion all the way down to a manageable size so that we can still use direct addressing? I mean, without going through a loop or without doing left child, right child, blah, blah, blah. Still kind of like direct addressing. You know, what would we have to do with our, what would we have to do with our 8-character words, you mathematicians?
Well, you can like take the big number that it gets you and then like divide it into a smaller number.
Yeah, that's exactly. Yeah, that's exactly the idea. Well, you take that big number and you design a what? What is it that takes one number and returns another number?
Function.
A function. All right. Does everybody see? You take a function. So here's the answer. What you do is you design a function. This is called the hash function, f of x, where x is a key. Are you with me? And what this function does is it returns a value in the range what? 0 dot dot table dot cap minus 1. All right? And then what happens is you take that big number that was with our key, you apply that function to it. That gets you down to this smaller number, and you apply f of x when they're accessing the table. So here is a picture. So now what we're going to do is we're going to modify it like this. So we start off with flapjack. That's 666C, 6170, 68, 61, 636B. That's that 7 quintillion, 300, blah, 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 blah. But now what do? F of that. And that's some function that we design. And suppose it gives us like 963. Then where do we put it? We put it in table sub what? 963. And if our table has, I just made this number up out of no significance to it, but if the table has 5,781, 5,782 entries indexed from 0 to 5,781, then it'll fit. And as long as this function is designed to give us a number within that range, boom. Now that is the key idea of hashing. That's what a hash table is. It depends on a hashing function to get our key down to a size that's small enough to fit into our table. Does everybody see? That's the idea. Now, with that in mind, now what do our algorithms look like for insert and the others? Now when we say insert key value, we do what? Table sub what? Not table sub key, but table sub what? F of key. Gets the key. Is everybody clear? Does everybody see how that works? This is all, I'm telling you, it's only about a half a dozen lines that you have to program for this project, but it's all conceptual. So this is the concept. I mean, it's a very short programming, but very conceptual. Okay, so and these are the concepts. Are you with me? Okay, and then how about the remove? It's the same thing. To program remove, you don't say if table sub key equals a special empty pair. You say table sub what? F of key. You apply the hashing function to it. All right, and then same way with all of them. That's the way it is. But still, no loops. No loops. Now, but there's a problem.
Something could have the same.
Yeah, say it again.
Two things could have the same function key number.
Yeah, does everybody see what the problem is? Because look, if you have this table that is, humongous, and each in direct addressing, each key has its own slot. If you're going to reduce the size of the table, now what happens is each key does not have its own unique slot. In fact, it's mathematically impossible for each one to have its own slot. So that means two of them must happen to at least some of them. They must hash into the same slot. See, so that is called the collision problem. And this next slide illustrates the collision problem. Now let's take a look at how this collision problem looks in this example. So suppose, oh, by the way, now that we're going to do this hashing thing, we might as well not have a limitation on the number of characters in the key, right? Because we're going to hash it anyway. So they can just be as long or short as we want. Are you with me? Okay? Because we're going to hash them all down anyway. So look, so suppose that your key is hippopotamus. And then suppose when you, oh, and by the way, our hash table now is denoted HT instead of table, and it's indexed from 0 to 9, so there's 10 of them, right? And suppose that, just, you know, suppose that when you apply the hashing function to hippopotamus, you get 5. That means hippopotamus is going to be stored in HT sub 5, and F of elephant is 0, so that's going to be stored in HT sub 0. F of giraffe is 8, that's going to be stored in 8. But then F of ant might be what? 0, so the ant collides with the hippopotamus. Are you with me? And similarly, but the crocodile did not collide. But then the chameleon and the panda both collide with the hippopotamus. No, sorry. Oh wait, did I say it wrong? The ant didn't collide with the hippopotamus, the ant collided with the elephant. Are you with me? Does everybody see that? So we have we have to solve this problem. But now look. Do you see though, now let's think about this. Do you see though that if the table is really, really big compared to how many keys that you want to store, what does that do to the probability of a collision? The bigger the table for a given number to store, what does that do about the probability? It decreases the probability of the collision. Are you with me? So now we've got probability entering into this whole thing with the performance. Does everybody see how that works? But on the other hand, if it's really, really big, there might not be any collisions, and you'll still have what? Big theta of 1. And if you only have a few collisions, you'll have big theta of what? Approximately 1. That's why we said, can we still have big theta of approximately 1? Well, if we can minimize the collisions, then the big theta will still be approximately 1. Does everybody see that idea?
Why is it that a collision makes it no longer big theta of 1?
Well, it depends on how we're going to have to handle the collisions. It depends on how we handle the collisions. And so what's going to happen is, then we're going to have to make some comparisons, some string comparisons. Because they're colliding to the same, so we're going to have a way to compare those ones that collided. You'll see. Yeah, that was a good question. All right. Now, before we go any further now, let's get this concept of the load factor. The load factor is typically denoted by the Greek letter alpha, lowercase alpha. And the definition of the load factor alpha is alpha equals n over k, where n is the number of entries in the hash table and k is the capacity of the hash table. All right, so that's the definition of alpha. So let's do an example that we just did. So in this example that we did before, you see n is 7. Hippo, elephant, giraffe, ant, crocodile, chameleon, panda. That's how many entries. And 10 was what? The capacity of the, all right? So it's 70, the table is 70% full. Are you with me? That's what that means. It's just called the load factor. Is everybody good? Okay. Yeah, question?
That seems like you could put more than 10 things in.
Well, it depends on how you handle the collisions. Some collision handling, actually, as long as you ask, and with some collision handling methods, what you do is if it collides, then you look for another place in the table.
Oh, okay.
That's and we'll see that. But on others, you don't. So it depends on how you handle the collisions. So, in fact, these are the 3 numero uno primary considerations when you design or when you use a hash table that's provided you by a library. The question is, there's 3 questions. The first question is the one we just encountered, the problem we just encountered. How are collisions handled? The second question is, what is the hash function, f of x? And the third question is, what is the capacity of the hash table? All right, and some of these things are interrelated, you know. There's trade-offs with how you set everything up depending on your application when you use a hash table. All right? And so we're going to look at some of the trade-offs and some of the issues that are involved in these 3 things. So now the first thing we're going to look at is collision handling techniques. Actually, here's the answer to your question right here. There are 2 primary collision handling techniques. The first technique is called chaining with linked lists. All right? And with chaining with linked lists, what you do is, instead of having, we'll see in detail how this is going to work, but instead of having the hash table be a hash table, instead of the table being a table of key value pairs, it's a table of linked lists. And then when you collide to the same one, you just put it in the linked list. Okay, and the linked lists are called chains. And the other way to do it is to have it's called open addressing with a probe sequence. And the way this works is, if you get a collision, like if you hash to a particular spot in the hash table and it's occupied, then you probe. And you could either probe the next one, maybe the next one down, and if that one's filled, the next one down from that, and if that one's filled, the next one down from that. That would be linear probing. Or you could do quadratic probing. If it's filled, you try the next one up from that. If that's filled, you try the next one down from that. If that's filled, you try the fourth one up, and then you try the fourth one down, and then you try, eighth one up, or sixth, or whatever. You see different. You try to. Okay, and then there's double hashing. If you hash and it's filled, then you hash again, and you get another. So, and all the open addressing, a characteristic of the open addressing ones is that you can eventually fill the hash table and have no more room. Okay. Now, what we are going to do in our project is we are going to use chaining with linked lists. That's what we're going to do. Okay. So here's a picture of how to resolve the collisions with chaining. So what happens now is that our hash table, HT, is now a hash table of linked lists. And when the elephant collided with the ant, then they just go on the linked list together. Are you with me? And then when the crocodile didn't collide with anybody, but the hippo and the panda and the chameleon all collided, so they're just on this linked list together, and then the giraffe. So everybody see how that works? Yeah, question?
So is this table full?
Well, this table can never be full, because with a linked list, what we're going to do is we're going to use the list L, and when it gets a new node, it just gets it from the heap. So as long as the heap is fine, we can just keep adding. So that's a benefit of using chaining to resolve collisions, is that you have this, you can draw from the storage from the heap. Yeah? So that was a good question. Okay? And now, here's an interesting observation. Do you see then that as far as performance is concerned, what matters is how many comparisons that we have to make, right? So look, do you see then that the average number of comparisons that we're going to have to make is equal to the what? The mean length of the chain, right? You see what I'm saying? What's the average? What's the length of the chain at HT sub 0? What is its length? 2. What is the length of the chain at 1? 0. What's the length of the chain at 5? 3. What's the average length? Do you see what I'm saying? What is the average length over the whole table?
You add all of them up.
You add all and divide by the number. So here, let's do that. So let's add them all up. It's 2 plus 0 plus 1 plus 0 plus 0 plus 3 plus 0 plus 0 plus 1 plus 0, and all that divided by what? 10. And you see that's the average length of the list? But look, what is 2 plus 1 plus 0 plus 0 divided by 10? That's what? 0.7. But wait a minute. What is 0.7? That's that. Yeah, it turns out that that's the load factor. It's the same thing. With chaining, the mean length of the chain is the load factor. And here, the thing of it is that this has a big, we're not going to prove it, but there is a hash chain performance theorem that says, let alpha be the load factor of a hash table with chaining for collision resolution. The asymptotic runtime for an unsuccessful search is big theta of 1 plus alpha, and also for a successful search is big theta of 1 plus alpha. By unsuccessful we mean you're searching for something that's not in the table. And for successful we mean you're searching for something that's in the table. But in both cases it's big theta of 1 plus alpha. Now you see, in order for your hash table to be efficient, alpha should be what compared to 1? small compared to 1. It's usually much less. You want to use your hash, you want to have your hash table have the load factor be like 10% or 20 or something like that, way down there, right? Because that means that what? That means most of the times that you go to the hash table, you're doing what? No collisions. So that minimizes the probability of a collision. So that increases your performance. Does everybody see how that works? So it's this weird 1 plus. The reason it's 1 plus alpha is because this alpha is a fraction that's much less than 1. So we can't say, oh, this is alpha, because it's not asymptotic. Alpha is not a number that gets asymptotically large. Do you see what I mean? So we can't say big theta of 1 plus alpha is big theta of alpha. Well, I mean, unless it does get large. How could alpha how could alpha get really, really large? If you do what?
At a small capacity.
Yeah, if the number of keys is way bigger than the capacity of the hash table. That's normally that's not the way you because once it gets that big, then you're losing the you're losing the asymptotic benefit of. I mean, you're losing the benefit of having the hash table have performance approximately 1, big theta of 1. Does everybody see how that works? Now, there are two DP4DS distribution hash table projects. There is a dictionary hash. And the dictionary hash is full-bore, complete key-value pair of dictionary implementation. It uses the list CSV project for the chains. It stores CA metrics for performance and data collection. But then there's another one that we have named hash data. And it's just, all this key-value pair doesn't really, we've done key-value pairs before, right? Why keep doing key-value pairs? From now on, we're just going to do the key part. Are you with me? And so hash data it just stores only the keys, and it's just to make the program simple so that we don't have to deal with key value pairs anymore. But you understand that in a real hash table it would be done with key value pairs, and you can look at the code for the dictionary hash to see how that would be done. All right, but the one we're going to use that you should install next is the hash data project. And what it does is it uses list L. So your list L project has to be debugged. Okay, so you need to put that in your include path, when you set up the project. And it's going to use list L project for chains. And furthermore, it's going to use our old friend CA metrics. CA stands for what? Comparison and assign. So we're going to take data on our hash table. And so now, and one more thing before we do the demo. Let me just mention, tomorrow we're going to learn about these two different hashing functions, the Knuth and the Bernstein hashing functions. And so this project that we're going to take a look at, it's going to ask us which hash function that we want to use, and we'll have a choice. And those are just the names of two different hashing functions, and we'll learn about that tomorrow. But let's take a look now at a demo of the hash data project. Okay, so now, before we actually get into the demo itself, there is some documentation. There's some documentation here about a file that I have provided for us to use. And I have put a collection of words in a file called words.txt, and that's a word list. And it's documented here. I got it off the internet. It's an open source project for dictionary words. And the open source project that I got it from was this 12DICTS, the 12dix word list. And there's a little preamble here that I put on the documentation. I modified it a little bit because the words only started with letters. They didn't have any numbers in them, so I added a few words with, and by the way, these are like the character numbers, the character values of the numbers. Were added at the beginning of the list. And the other thing I did is so that we could use it with key value pairs, I appended some random integers at the end. I appended a random integer at the end of each word so that we could have a key value pair. The key would be the string and the value would be the integer. Although, like we just got through explaining, the hash data one ignores the value part anyway. But anyway, so that's some information about the words.txt file. Okay, so here we are in NetBeans, and here, just to show you the content of that words.txt file, it's up here. See, look, I think the Word file started here on line 6. Abac, abacus, abandoned, abandoned, abandonment. And I added this 1, 23, 4, 56, 78, 9, 10, BMW 325i. And look how far this goes down. All the way down from there down to what? Zucchini. From aardvark to zucchini. And that's, look at how many, that's 21,882 words. All right, so we have this in order to run our hash stuff on. Now check out what our hash data project does. Now watch this, let's just run it. Okay, so here we are running, now watch, it says hash function type, Knuth or Bernstein. So here let's just do K for Knuth. Size of hash table. Now let's make it something like, I don't know, 10 maybe. And number of keys to load, let's say 5. Load from what file? And what was it called? Words? .txt. You got to put the .txt or it won't take it. And let's display loaded keys. Let's say yes. And so there's the loaded keys. These were from the first of the file. Remember, it was 1, 23, 4, 56, and 8. Dump the hash table. Yes or no? Yes, we want to take a look. And look, there's what happened. Now, can you tell what happened with the hash table? It put the 456 hashed at what? HT sub 2, the 78, 9, 10 hashed at 4, the 1 hashed here, and the 9 hashed. Oh, but there was a what? There was a collision. Now, do you see the collision there? Are you with me? Display tested keys? Yes. So now here it gives us all the statistics. Now, here's what it does. First of all, we said 5. So what it did is it installed 5 of them, all right? And then when it tested them, it tested those 5 plus the next 5, because we wanted to have some tests with a successful search when the data was in there, and also some unsuccessful ones when it looked for something that was not there. Now, does everybody see the concept there? Are you with me? And look what it gives us. It summarizes this. It gives us the hash table type, the hash type, the hash table size, the number loaded. See, it loaded 5. It always tests double what it loads. Are you with me? And the number found, this had better be however many got loaded. Are you with me? Because if everything's working all right. Number of found. Now here's how many comparisons it took to find. So the number of found comparisons was 6. Found comparisons per query was 6 divided by 5, which is 1.2. Number missing 5. Number missing comparisons per query. And here it gives you the what?
Load factor.
The load factor. Okay, so look, let's run this again. You can do all kinds of really interesting experiments with this. Look, let's do the Knuth again. Size of the hash table. Let's still say it's 10. This time, number of keys to load. Let's load 10. Load from what file? Words.txt. Display keys, yes. Now, see, it's getting some of those other ones. Dump hash table, yes. Yeah? Oh, now look at these. Do you see what it used? Hashed into 1, 2, 4, 5, 7, and 9. And look at those collisions. A collision occurred here, a collision occurred here, here, and here. Display. Are you with me? You see how that works? Now look, you can do really big ones. Check this out. Let's just say, oh well, let's go ahead and no, let's not do that. Okay. Now look, you can do really interesting experiments. Check this out. Hash table Knuth, size of hash table. Let's make it like 1,000. Right? Number of keys. So let's just make it like 20. And then load from what file? .txt. Display loaded keys, yes. So those are the 20 keys that are getting, and dump the hash table, yes. Now watch. Look at this. What happened? Because it was 1,000, and look, they hashed all the way from 12 up to like 947. And what do you notice here? No what? No collisions. Are you with me? So see how that gives you all that info, right? So let's say no. And there it gives you all the data. All right, so that's our end of demo. And now you guys, I think you have enough to actually start your coding tonight. because even though we haven't learned how to do the, how to write the hash functions yet, I think you can still start working tonight. Now, so here's the thing. Well, maybe. Maybe that was optimistic. Okay, first of all, what we're going to do, the way we're going to implement this, we're going to do a little code walkthrough now of the code in the hash data project. First thing we want to point out is that this project uses the functional programming features of C++ 11. Those of you who are in programming paradigms know that the very first one that we did was functional programming. And what did we learn about functional programming? You can have a variable of type what? Function. So in C++, you can have a variable of type function. So it declares a hash function to be a type. And furthermore, a variable can have a function type. And not only that, but you can pass a function as a parameter. And so this uses all those features of functional programming. So now let's take a look here. This next slide from the hash data project sets up the two hash functions, the Bernstein hash and the Knuth hash, right? And take a look at this code. It's quite interesting. You see here, you see the second line, it says type def function unsigned int CA metric string constant ampersand hash function. Now this is defining the function type. All right, this is setting up a type. This is the type def feature. In the same way that type def CA metric bracket string is capital CA metric string, that defines that type. This defines a function type. Are you with me? Does everybody see that? And now look here. This is a function. This Bernstein hash is a function that has the same what? The same specification that this type is. Because this specification here says what's in the parameter list. What does it return? An unsigned int. Bernstein hash returns an unsigned int. Okay, does everybody see? So this is a hash function. And what's another hash function? Knuth hash. Are you with me? So we got these two different functions that we want to be able to execute at will. And now here, check this out in the main program. In the main program, what happens is, so we have int main, we have some statements, and now what do we have here at the top of the main program? We have capital H hash function, lowercase h hash function. So what is that capital H? That is a type. It's a function type. And what is this saying? This is saying that lowercase h hash function, a variable has type function. Are you with me? Does everybody see how that works? This is so cool. Now look. And down here, remember it prompts us for the hash function type? Okay, so look, what is this? Oh, so we have a string, function name is the response. And now he says, if response equals, if the first letter of the response is lowercase k or the first letter of the response is uppercase k, what does it do? Hash function gets what? Knuth hash. So here is the variable gets the function. Are you with me? The variable gets the function. And furthermore, down here what happens is, when we go to set up our hash table, this is the constructor for the hash table. And what does the hash table have in it? What does the constructor take for the hash table? It takes the what? The table size and the what? The function to use. Are you with me? Ah, oh, this is so excellent. All right. And then here, so here is the hash table. Here is our hash table code. So class hash table, and check this out. What happens is, you see, what does a hash table have? It has a what? An underscore hash function, which is a what? Capital H hash function. Are you with me? As an attribute. Are you with me? And you see down here in the constructor, you see how underscore hash function got set to hash function. Are you with me? And then what is the hash table itself?
An array.
An array T of what?
Linked list.
Of lists of list L of symmetric string. So HT is the hash table. Now here's what you can do. Actually, you can do the code from that. Here's what I recommend you do. If you now know enough to code everything except the hash function. What you should do is comment out or throw out the CERR and the throw -1 and just say return 5,000 or whatever. You see what I'm saying? Then you can then that should compile, and of course you'll always be returning 5,000, so there will be a collision every time, right? You see what I'm saying?
Oh, on the hash
You
function.
see on the hash, yeah. But still, just before you can, so that you can test your program, just do that, and then down here in the hash function app. Here, oh, by the way, the only thing that we're going to do is insert and contains. We're not going to do remove. Okay, so anyway. And here, these are just short little one-liners. I think you can get those to work, even just with this one lecture under our belts. All right, good deal. Sorry I kept you a little bit late. See you tomorrow.